In the third module, we're going to focus on oxygen uptake, the cardiorespiratory responses to exercise, and the limits to VO2 max. As we saw in the last module, the oxidative metabolism of carbohydrate and fat is very important for supplying energy to muscles during prolonged exercise. And in parallel with that, there needs to be an increase in the oxygen delivery to the contracting skeletal muscle so that the mitochondria are adequately oxygenated in order for these metabolic reactions to occur. So we're going to focus in this module on the cardiorespiratory systems and how they ensure that oxygen delivery is maintained during exercise. Important principle is that the oxygen uptake is directly proportional to the exercise intensity. The efficiency of conversion of the metabolic energy into mechanical work is relatively constant, at least during cycling exercise. So for a given power output, there is a fairly constant VO2. And you can see here, for various power outputs, as you increase the exercise duration, there is a characteristic VO2 associated with that power output. So if we plot VO2 against power output, we see a linear relationship, which is fairly similar between trained and untrained subjects. As I said, they're relatively similar mechanical efficiencies across a range of training status. Eventually, you reach a point where the oxygen uptake cannot increase any further, and we refer to that as the maximal oxygen uptake. We'll come back to that point later in this module. If we look at the time course of changes in oxygen uptake, from rest to exercise at a given exercise intensity that requires a given oxygen uptake, we refer to this as the steady state. We can look at the kinetics of the increase in VO2 with exercise and the decrease in VO2 after exercise. You can see here that as VO2 increases up to this steady state level, there is a lag in oxygen uptake, and that increased energy utilization that's required in that transition period is met by the other energy sources. This is referred to as an oxygen deficit. Interestingly, oxygen deficit, or the maximal oxygen deficit, has been used as a marker of anaerobic capacity in an applied sports setting. During exercise, as long as that exercise continues, there's a given oxygen uptake. And when exercise stops, there's a rapid decline in the VO2, but it remains elevated for some time. And this may include several hours, depending how hard and how long the exercise is. Initially, this period was referred to as the oxygen debt, and you'll see that term in many textbooks to this day. More recently, the preferred term is excess post-exercise oxygen consumption, which really summarises what's going on rather than ascribing any mechanism to the increased oxygen consumption. You saw this slide in Module 2 on fuels, but just to reiterate, during this oxygen deficit period, where there's a difference between the oxygen requirement of steady state and the actual oxygen uptake as exercise commences, that increased or that energy difference is met by utilization of phosphocreatine and the glycogen to lactate system. There's been some interest in trying to understand why there's an oxygen deficit. You could imagine that it might be due to a lag in oxygen delivery. It takes some time for the cardiac output, for the muscle blood flow to increase, and for the oxygen to diffuse into the skeletal muscle tissue. Alternatively, oxygen delivery might increase quite quickly, and the lag might be due to sluggishness in mitochondrial respiration. And of course, it's possible that both systems might be involved. A number of experiments over the years have tried to identify, is it oxygen delivery, is it oxygen utilization? And depending on the exercise intensity and the situations of those experiments, results have been obtained in support or against either mechanism. So probably both contribute to some extent. During exercise, as I said, at a given exercise intensity, there is an oxygen requirement. At lower exercise intensities, you can see that there's generally a levelling off in the first few minutes of that exercise. At higher exercise intensities, however, it's not uncommon to see a slow upward drift in the oxygen uptake. This has been modelled, and there's a fast component and a slow component. And so you'll often see the term slow component referring to this slow drift in VO2 over time. And during prolonged exercise, there is a general upward drift in VO2. What mechanisms might contribute to this increase in VO2? Well, most of it is due to changes within the active muscles themselves. 80, and in some studies as much as 90 to 100% of the increase in VO2 during prolonged exercise at the whole body level can be attributed to changes in the active muscles. Some of the changes in skeletal muscle that contribute to that include recruitment of lower efficiency type 2 fibres, changes in the efficiency of ATP production to oxygen consumption, an increase in muscle temperature, an increased reliance on free fatty acid metabolism, which tends to have a higher oxygen requirement, and elevated catecholamines, which can impact on metabolism. Factors outside the muscle, which could contribute to this increased oxygen consumption, include an increased oxygen requirement of the ventilatory muscles and of the heart as they increase their activity during prolonged exercise. If we look at the post-exercise period, there are a number of processes going on that are thought to contribute to the maintenance of a slightly higher VO2 during recovery. In the fast component, or that rapid decline early after exercise, it's generally agreed that the resynthesis of creatine phosphate and the restoration of the myoglobin oxygen stores account for most of that extra oxygen consumption. In the short to medium term after exercise, heart rate, ventilation will remain slightly elevated, and that will increase the oxygen requirement. There'll be an increase in temperature, which is maintained for some time after exercise, and that might also contribute to a slight increase in VO2. We know that there's an increased free fatty acid metabolism during recovery, and that might contribute to this increased oxygen requirement. Also, mitochondrial uncoupling, or again, a change in the ATP to VO2 ratio might contribute to a need for higher oxygen uptake. And in the longer term, there's resynthesis of glycogen that's been utilised during exercise, and the synthesis of key proteins that might contribute to the adaptive response to exercise. And these are energy dependent. If we look at creatine phosphate resynthesis, which is occurring in this early recovery period, this is a process that occurs very rapidly. The half time is in the order of 60 to 90 seconds, which means after 60 seconds of recovery, you've restored about half of your degraded creatine phosphate stores. It is dependent on oxygen availability. If you occlude the circulation and prevent oxygen being delivered to the muscles, you prevent the resynthesis of creatine phosphate. It's dependent on the muscle oxidative capacity, and this is often, or the resynthesis of creatine phosphate is often used as a marker of oxidative capacity. In this study, you can see a modelling of the rates of creatine phosphate resynthesis, and here a relatively slow resynthesis, and in these subjects a faster resynthesis. And the differences there are largely due to differences in the oxidative capacity. The higher the muscle oxidative capacity, the faster the resynthesis of creatine phosphate. And finally, one of the reasons why many athletes supplement their diet with creatine is to enhance the resynthesis of creatine phosphate. And this is important for high-intensity repeated sprint efforts. One aspect of the original oxygen debt hypothesis that has received some attention is the fate of lactate, and it was thought for many years that the oxidation of lactate contributed to the extra oxygen consumption during recovery. It turns out that this is not the case, and that oxidizing lactate really doesn't contribute or increase the VO2, nor should I add, is there good evidence that it contributes to muscle soreness. It is well recognised, however, that oxidation of lactate is a major metabolic fate in the recovery period, and lactate can be taken up and oxidised by the type 1 skeletal muscle fibres. One of the effects of training I indicated was an increase in MCT1, which will facilitate the uptake and the subsequent oxidation of lactate. And cardiac muscle, with its well-developed oxidative capacity, can oxidise lactate. An active recovery, where the slow-twitch fibres maintain their metabolic rate during exercise, can facilitate the lactate removal, particularly, or notably, if the exercise is below the lactate threshold. Lactate can also serve as a substrate for glycogen resynthesis and also for gluconeogenesis, and some of the lactate can be converted to other metabolites such as amino acids. The other key metabolic process during recovery, certainly in the hours, certainly up to 24 hours after exercise, is the resynthesis of muscle glycogen. The factors which influence this include the degree of muscle glycogen depletion and the extent to which glycogen synthase, a key enzyme in glycogen synthesis, is activated. It's also dependent on the expression of a glucose transporter, GLUT4, which transports glucose into the muscle cell. And the blood glucose and the plasma insulin levels are also very important after exercise, and these are determined by the extent to which carbohydrate is ingested, influenced by the amount, the type, and the timing of that carbohydrate ingestion. Muscle damage after very prolonged strenuous exercise, for example, such as a marathon, has been shown to slow the rate of glycogen resynthesis.